Hello guys, welcome to my channel. So this is a video which I would say is more for math nerds like me. So I am a math nerd. I like doing maths. I like to explore things in maths. And in today's video, I will be basically, I won't say exactly prove, but I would be just doodling with Euler's formula, which is like one of the most elegant, most beautiful of the formulas in maths that basically lets us think that, okay, this is why maths is great. So stay on and hopefully you will also learn something from this video. And one of such formulas that I want to talk about today is goes on like this: e to the power I pi equals to minus 1. Or you could also see somewhere e to the power I pi plus 1 equals to 0. Both basically just rearranging the terms, but so this is a very elegant formula, right? And once you see it, you see like, okay, how such terms which are very crucial in mathematics, like e is a very crucial term, I, pi, every each of them are very crucial, and how they are related with each other. So this is very good to see. But how this formula came to about, so how exactly you can find this formula? So just a little tidbit of information that I want to show, to do a little proof. So it's not a rigorous proof, it's just some fun video for mathematics nerds like me, right? So how do we get to this place? Before this, let's basically revisit some of the basics that we will require for actually getting to this point. Like everyone should know what a power means, right? Like, say for example, if I say x to the power y, what does that actually mean? It means that you multiply x y times. So you multiply x multiplied by x multiplied by x, and you go on for y times. Here y can be any term, obviously. So it can be negative, it can be positive, but there's some interesting thing. Like, say for example, if y is 0, that's a very specific case. Like, if for any x if y is 0, we assume that it would be 1. So this is kind of a definition in mathematics. And similarly, so e is also a irrational number, right? E is an irrational number, which we use in logarithms and in so many other fields, right? And so there's another thing called Taylor's expansion, right? Why I'm actually mentioning these things in a fragmented way, because these all basically come together to give you this beautiful formula. So Taylor's expansion, I won't go into a lot of details, but what Taylor's theorem basically says is that you can basically convert any function which can be differentiable for any number of times. You can convert that function into a sum of polynomials. And if you can convert a function to a polynomial, if you can convert any function to polynomial, that's a great help in solving a lot of things. And not only that, but in computational science specifically, it is of great help. And you can do a lot of approximations with this kind of expansion. So these are usually infinite series expansions. And so the general formula goes on something like this: like f of x is equal to, and so on and so forth, right? So it's an infinite series, so it goes on. So basically f of x can be written as f of a plus f dash x. So f dash basically means differentiation of the function f of x with respect to x, multiplied by x minus a, the difference, divided by 1 factorial. So 1 factorial again, n factorial again is a term in mathematics which means n into n minus 1 into n minus 2, and so on and so forth up to 1. So this is Taylor's expansion, a general form of Taylor's expansion. And if you basically center one function on zero, so like if you basically tells a equals to zero, you find some specific form of Taylor's expansion, right? And using that actually you can find the expansion of sin x and cos x, which are basically used in computational sciences, right? So if you are into programming, if you ever program sine of a number, sine of 3, sine 4, sine 5, any number if you want, you would see a number, right? You see a result. How do you actually get to that result? Because the computer needs to know an approximation of that particular formula. Usually when we are in schools, we just actually read very specific sine data, right? Like sine 30 or pi by 6, which is half or something like that, or sine 45, like pi by 4, sine pi by 4 equals to 1 by root 2, things like that. But how do a computer can measure something like sine 25.8 degrees, right? So for that you need a proper functional form of sine x. And from Taylor series expansion we find that, so for sine x, the Taylor series goes something like this: x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus x to the power 9 divided by 9 factorial, and so on and so forth. It goes on like this for infinitely, right? So this is the expansion, Taylor expansion for sin x, and similarly for cos x, you can write something similar, right? You can write cos of x equals to 1 minus x squared by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial plus x to the power 8 by 8 factorial, and so on and so forth, minus, and it goes on like this. So why I'm writing this? Because now you can find some similarity between the formulas of sin x, cos x, and the other thing that is in the Euler's formula is natural logarithm, or e, right? So e can be written, or e can be defined as something like this. Like if I have e to the power x, we can write it as 1 plus x by 1 factorial plus x squared by 2 factorial plus x cube by 3 factorial, and so on and so forth. So it goes on like this. And a good thing about it is this formula, this is defined such that x can be anything. Like x belongs to complex number set. So x can be anything. It can be a complex number, and as you know, like real number is a subset of a complex number. So x can be any number, and this formula holds true, right? So now, once I actually write down all these three formulas, you get to see some similarities, right, between this kind of Taylor expansion series formulas. And if I zoom in, you can see like sin x is like x minus x cubed by 3, x minus x to the power 3 divided by 3 factorial plus x to the 5 by 5 factorial. Cos x is something similar. It has like all the alternating powers, and e is kind of like accumulation of both of these, right? So let me do one thing. If we start writing this thing, I of sin x. So if I multiply every term of sin x with I, and what is I? I is basically kind of the unit of complex numbers, right? So I square is equal to minus 1. So I is written as root over minus 1, which is kind of the basics of complex number, unit of any complex number, complex portion of a number. And you could also write, like, since I square equals to minus 1, so you could write I to the power 4 equals to minus 1 square, that is just positive 1 plus 1, and I cube can be written as I square multiplied with I, which is minus I, because I square equals to minus 1. So you get I cube equals to minus I square equals to minus 1, and I to the 4 equals to 1. So if I multiplied every term of sin x expansion with I, you would find something like this, right? I into x minus ix cube by 3 factorial plus ix to the power 5 by 5 factorial, and you get the picture, right? And now I can write it like this. Let's write it like this: ix, and then minus ix cube divided by 3 factorial. Let me write it like this: ix whole cube divided by 3 factorial. Why I can write it like this? Because once I make it out of this parenthesis, x to the power 3 and I cube, right? So ix whole to the power cube will be I cube into x cube, and I cube, as I just shown you, it's just minus I, right? So we get minus ix cube divided by 3 factorial. Similarly, I can write it ix to the power 5 divided by 5 factorial as ix to the power 5 divided by 5 factorial. Why again? I to the power 4 is just 1, right? So I to the power 5 can be written as I to the power 4 into I. So just for brevity, let's show it. I to the power 5 is I to the power 4 into I, which is 1 into I, which means I. Easy, right? And you would see like everything, like the next term was minus ix to the power 7, right? Divided by 7 factorial. So this can be also written as ix whole to the power 7 divided by 7 factorial. Why? Because again, if I want to show what is I to the 7, I to the 7 can be written as I to the 4 into I cube, because as you know, x to the power y into x to the power z can be written as x to the power y plus z. Uh, right, so due to this, you can write I to the 7 as I4 into I cube, and this is basically 1 into I cube, basically minus I. So this is minus I. So I to the 7 is minus I. So you can write it like this. So as you go on, you can see, right? So I sin x can be written something like ix plus ix cube by 3 factorial, x5 by 5 factorial. And similarly, now I can write cos x a bit differently as well, right? So let me again. So even cos x, which is, as you can see, in the previous term, it was like 1 minus x squared by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial plus x to the power 8 by 8 factorial, and so on, right? And now I can also write it like this: 1 plus ix whole square divided by 2 factorial. Why? Because I square is again minus 1, so it will be I square x square means minus x square. Then again I can write ix to the power 4 divided by 4 factorial. This is again self-explanatory, as I just showed you, like I to the power 4 equals to plus 1. And similarly, I can write I to the power x whole to the 6 divided by 6 factorial, and so on and so forth, right? So it would be again plus ix to the power 8 divided by 8 factorial. So what does it mean is, now if I add these two, right? So I have written sin x in terms of I sin x in terms of ix, and cos x also in terms of ix. So now if I, let me put another big divider here, and if I just start writing cos x plus I sin x, because you remember, right, I multiplied sin x formula with I, and now you get something very similar, right? 1 plus I also rearranging, so you would get something like 1 plus ix plus ix square divided by 2 factorial plus ix cube by 3 factorial plus ix4 divided by 4 factorial, and so on, right? So if you just see beforehand, so the first term is from cos x expansion formula here, Then the second term is from the sin x formula. Just pulling it up. Yeah. Here you got ix, then ix square by 2 factorial, again from cos x, again from sin x, I sin x, again from cos x. So you basically, once you add these two up, cos x and I sin x, you get a full formula like this, right? 1 plus ix plus x. And now this looks familiar, right? Because we saw e to the power x formula, and it seems like e to the power ix, right? So instead of e to the power x, so if I just go back a little bit, you saw this formula, right? E to the power x equals to this formula, right? Let's border with red. So e to the power x equals to 1 plus x by 1 factorial, x squared by 2 factorial, plus x cubed by 3 factorial, and so on and so forth. And now, if you just replace x by ix, you see the same formula over here, right? So there we have already called almost cracked it. So what we found? So we found that e to the power ix. So e to the power ix, it can be written as cos x. Let's put it in bracket for so that there's no confusion. Plus I into sin x for any x, right? And now we are almost complete, because now if we just since we say that this formula holds true for any x, if we just assume x equals to pi, then this equation basically becomes e to the power I pi equals to cos of pi plus I sin pi. And as you know, sin pi is equals to basically 0, and cos pi equals to -1. So you go with e to the power I pi equals to -1, or you can alternatively write this as e to the power I pi -1 equals to 0, and here it is, Euler's formula. So this was very kind of a small proof. I won't even say it's a proof. It's just showing how these things come together and basically actually make another great formula out of it. So you have to know some things like, okay, what's the Taylor expansion for say sin x, cos x, e to the power x, how do you define? Some comes from the definition. If you are interested about knowing more about how exactly Taylor's expansion came into being, so you have to read about the fundamental theorems of calculus, right? So if you read about say mean value theorem, for the second fundamental theorem of calculus, you can actually derive Taylor's expansion from those, right? And through these all these you can see like how these quantities, the quantities with great importance, which is basically the base for natural logarithm, I, which is basically kind of the unit of any complex numbers, pi again is the ratio between the circumference and the diameter of a circle. So all these numbers which have like significant meaning and importance in mathematics, they all come together, and this is a great formula that they appear into. So this is called Euler formula. This is kind of how you can derive at it. Hope you like this video. Let me know about it if you want to see more of this kind of this video. Thanks so much. Thanks for watching. Please like, share, and subscribe if you like this video. Thanks.